Now let's look at some issues that you may face if the structure that you declare and define for memory access is not aligned properly. So far we have looked at uh, a structure which is properly word aligned. So when we were accessing the different registers from the memory location, the structure did fine. But there could be issues, there could be scenarios where the structure that you have declared may be out of alignment. And in such a scenario, there is a fair possibility that what you wish to extract will not be what you actually extract. Okay? So there will be the data that will be extracted by the structure is wrong. This is a different C file, which is structure underscore padding.c, which is this part. The global part is pretty much the same for that structure, but there are certain small differences, and because of which I have kept these two files separate. So to now uh, debug this particular file, you need to go into the makefile. So if you do not understand makefile right now, not do not worry, because we are going to have a chapter entirely dedicated to linkers and makefiles, so you will understand what is happening here. But nevertheless, as of now, just change this line to the C file name, that is struct padding.c. So since we are working on a makefile project, the IDE is going to refer to the makefile to build the project, and the makefile has been written by the developer. So the IDE is not using its own makefiles to build this project. It is using the makefile that is written by you. So anyway, so you have let's name it struct padding.c. So this is the file that we are going to now look into. Now let's look into the file. So this is the first change you have to do. So let's close this one and look at struct padding.c. There's an array of 16 8-bit values or 16 char values that you can see here, all hex values, and we are going to use this array to demonstrate the problem with struct padding. And we have declared three structures, and they are pretty much the same. All these three structures are very same to look at, but then the type of each of these variables have a different data type. So in the first structure, the data type is first one is an 8-bit value, second one is a 16-bit value, third one is a 32-bit value, and the fourth one is a 16-bit value. In second structure is again second structure is the same as the first structure. The only difference is this structure has a packed attribute, and we'll see what the packed attribute does. Third structure is completely aligned. Okay, so we have declared the elements in the structure in such a way that it is aligned. So we will have a look at all of this one by one. So what we'll try to do is we will consider these elements of the array that we have declared as memory locations, not the elements, but the indexes of this array as memory location. So this is index 0, say memory location 0, index 1 is memory location 1, 2, 3, 4, 5, 6, and so on. Okay, let's imagine that for the time being. So this is nothing but, say, this is like a memory location. So 0 comes here, and then you have the first byte, second byte, third byte, and goes up to the 15th byte, or byte number 15, 16th byte. Okay, so what we have here is, say, address location 0, 1, 2, 3 to 15, and it has AA, BB, CC, DD, and so on. Okay, so let's assume this as a memory location. What we have to check here is we will assign this particular array to each of these structures. So we actually saw how to assign a memory location to a structure previously. So we'll just do the same. So this is the data buffer. So we've called it a data buffer. So ampersand data buffer. So here we are not assigning exact addresses like previous, because this is just for demonstration. This is just for demonstration purposes, to show you the problems faced with otherwise it is different. Okay? It is not an address location as such, in the sense it is not a peripheral address location as such. It's just the address of this structure, address of the array. So what we do is memory map align. So these are again, I've named them differently. So one is called memory map aligned for the structure which has an aligned memory map. One is unaligned but it has a packed attribute. Another one is a unaligned and not packed. Okay. So we will see this structure first, that is memory map unaligned and not packed. So memory map unaligned, and so let's use this one first. So let's change. So we have, what do we have? Let's go through the main and we have so we'll change all these names. So this is just declaring a pointer like previous here of one of these type defs, and then extract data is a particular variable, and we are which is of the type this memory map aligned or anything, and then we are assigning the address of the data buffer that we saw on top to this pointer, and then we are accessing this pointer one by one. Okay, we are checking the size of that particular structure, and we are accessing the structure one by one. So what we can do here, just to make our life a little easier, is we will so we'll do hash define struct equals, and in this hash define line we are going to change the structure names like memory map aligned and so on. So all these declarations and whatever names we have, we will be changing it here in one place, and all of them will be getting and this is going to reflect in all the places. So why not make use of a macro to make our lives easy? So it is struct star. So here we again do struct. Let's not have this define and data and all that. We have seen this before, so we'll not keep it. So struct star and extract data. So what happens here? We do size of struct. So I hope you're following what I'm doing. I don't want to repeat the copy the name of that particular structure over and over again. So I'll just put the name here once, and then this should trickle through the entire all the lines of code. Okay, so that's what I mean. And first, let us try with memory map unaligned and not packed. So what I'm doing here is I'm assigning the pointer of this particular array to this structure pointer, and then I am extracting all the elements. Okay, that is the first element, second element, third element, and the fourth element. And we expect the elements to be of a particular value. Okay, for example, let's say for the first structure, it's an 8-bit, 16-bit, 32-bit, and 16-bit, right? So when we are accessing this particular data buffer, so the first element 8-bit should be AA, and then the next element, second element is a half word, or yes, it is a half word. So it should get these two values, BB and CC. Then the third element is a word, full word, so it should be DDEEFF11, and the fourth element is again it's 16 bits, half word, so it should be these two values, 22 and 33. I hope you are getting it. So the first element is a char AA. It should get AA. Second element are the next 2 bytes because it's UINT 16 second element. So it should be these 2 values, BB and CC. This is how the structure maps to this. It's supposed to map to this address location. And since we have, and like we know, if you map a structure to a particular address, it takes that address location to be the same as the structure, right? So it can be any type of, it can be any data type, okay, like we saw previously. So the third element is again UINT 32, so it should be DDEFF11, and the fourth element is 16, so it is 22 and 33. Okay, so this is what we are supposed to get. Now let's see what we actually get. Okay, and then we will we'll explain the problem once we see a discrepancy. So now it's on debug. So, and let's single step through. So this is actually assigning the data buffer address to the structure, and then we go down, and then we have we print the size of the structure now. Okay, and the size of the structure comes to 12 bytes. So it is 12. Now let's count how many bytes a structure is supposed to have. See, 1 byte, 8, 2 bytes. So sorry, 1 byte is 1 byte. 2 bytes is 2 byte plus 1 byte is 3 bytes. This is 4. So 4 plus 3, 7 plus 1, 7 plus 2, 9 bytes. So this structure should ideally be 9 bytes, but it is showing it is 12 bytes. Okay. So why is this happening? It is happening because the compiler has padded this structure to align on a word boundary. So there are gaps within this structure. If you had created an actual structure and assigned elements, say you did a memory map and align not packed, and you created a structure out of this, and then you aligned you assigned values to these particular variables, then you will not see this problem. Okay, you will only see this problem when with whatever we are doing here, because if you fill up the structure saying first element, second element, third element, fourth element, then what you will see is the compiler is intelligent. It is going to, even though there is padding, it is going to assign those elements to the right variables here. But if you are mapping the structure this way, that is, you're just mapping an address location over to the structure does not know what to make of it. So it is not that you have specifically taken the structure and you have done this. So you have not done this. You have not done say first element. So structure dot first element and then some value. You have not done it that way, or structure arrow first element equals to some value. So even if the structure is even if the structure is padded, you'll get back the values that you have put in. But then this case is different. Here we are doing it. Here we are doing something different. So let's see. Let's step through, and maybe we'll try that out also on an unaligned structure. That is, we will fill some values to these in these variables, and when we extract the values, we'll see that obviously we will not be able to see the problem here. Anyway, so now we have so first of all, it is showing us 12 bytes, which is suspicious, and then we see what is the first element. So the first element is 170. Let us do a hex view. So 170 is AA. So it is AA here. So the first element has come up right. So next one is a 16T. That is it's a half word. So we are supposed to see BB and CC. So let's step through, and let's see what we see here. We see CC and DD. You see the problem here? BB and CC should have come, CC and DD has come. So it has skipped the BB location, which is not right. Okay, so this problem is going to cascade. So that is, next one, the third element will again have some other value, because it's pushed out. It will propagate the error. So the third element will be EEFF2211. Ideally it should have been DDEEFF11. Okay, but we have EEFF11 and 22 because of the padding issue, and the last element is again of course wrong. It is going to be, it is not what we intend to see. It is not what we intend to extract. So it is 33 and 44. So it should not come up to 33 and 44. So it should be, first one should be 0xAA, next one should be BBCC, then it should be DDEEFF11, and then it should be 22 and 33. So it is off by 1 byte, as you can see. So this value is off by 1 byte, and that is because there is some padding happening here, which we are missing. Okay, and the compiler is not confused here. We have not accounted for the padding of the structure. So how can we go around it? So one thing we can do is, so let's struct star extract data. Now let us do one thing. Let us on the same structure. Now what we do is we declare another, we create some struct space. Okay, so we create a struct with space. Okay. Now when we create a struct with space, so in this case obviously when we are filling values to this one, so we could let us keep it as a structure. Even if we declare it as a structure pointer, it's going to be the same, but let us keep it as a structure. So we do say, so here we are not referring to this particular array. Now we are trying to fill up, and this is a different structure, of course, right? So I hope you understand, this is only taking the structure declaration, and this pointer is of this structure type. This is a different separate structure entirely. Okay. So what we'll do is we'll do, say, struct with space dot first element dot second element dot third element dot fourth element. Or should we okay, let's do one thing. Let us declare it as a pointer only, so it kind of becomes more clear to you. So we'll do struct star, and this is I'm putting some random names. I'm not thinking much here. Struct star space data equal to, we'll do ampersand struct with space. Okay, so ampersand struct with space. So just put an ampersand here. So we are actually getting the address of the structure into this structure pointer. Now this pointer is again a different one. This is a different pointer. This is of course a different pointer, and it is pointing to a structure that we have created in the sense we have created space for the structure. This has got nothing to do with the array. So now let's assign values to this structure now. Okay, so let's assign so struct with space, control V struct with space, and then we'll assign some value to first element. So first element equals to whatever 0x a, and then it'll go on like that. So BB. So first element is a byte. So AA. So second element could be AABB because it is a half word. I think so. Yes, it is a half word. third one could be AABB BBCCDD. That's a word. And the fourth one could be, I will change this, the first, second, third, fourth element. I've not yet done it. So this is again half word. So AABB. Okay. Now, first element, second element, third element, and then fourth element. So I hope you are getting what I'm trying to do here. I'm just trying to show you that even if the structure is padded, if you use the structure in the conventional way, you are going to still get whatever values you're expecting, and you won't feel a thing actually. Okay, you'll feel the problem only when you are using the structure this way. That is, you are mapping it directly to a memory location. Nevertheless, let's compile this. Okay, errors. Let's see what. Invalid type. Okay, I'm sorry. This is going to be space data. I'm sorry. So that's the structure pointer, right? So yeah. Now we'll step through this and we'll see what space data gets. So space data is a structure, and you have the first element, second element, third element, and fourth element. So this is the structure here. Okay. So now it has junk. So let's do one thing. Okay. Now this program is not complete. So we are just feeding the values here. Let us extract the values as well, because otherwise we won't know that even if the values are fed there, and if we see the values in the structure in the debug. So I've created 4 variables here. That is first read, second read, third read, and fourth read, which is again reading back from the structure elements. And we will inspect, we will watch these variables. So one is 8-bit, another one is 16-bit, 32 and 16-bit. That is how the structure is laid out. So what I'm trying to demonstrate here is, even though the structure is padded, if you are actually accessing those elements, if you are writing into those elements and reading from those elements, you will not see the problem. That is, it will be fine, but only when you assign a memory location to that particular structure pointer, which is already existing, then you will begin to see issues. So let's put this on debug, and we'll see what, and it will make my statement more clear. So let's step through. So we are space data. So we are filling up this structure. So let's see. So we have filled up this structure, and it says 170. Yeah. So it has said first element. So let us view these as hex values, so that it is easier for us. So we had put AA in the first element, AABB in the second element, AABB CCDD in the third element, and AABB in the fourth element. So we can see that those elements have been populated. Now let's see if, when we are reading those elements out, if we are seeing the values. So let's see. So the first read is 170, that is the same. Okay, number format hex, so it's AA. Let's see what the second value is. Second value is, of course, this is, I know this is the same, but anyway, let's see. Let's convert it to hex. It is AABB. Third value is this one. So let's change the number format and AABBCCDD. And the fourth value is, again in hex, it is AABB. Okay, so as you can see, the values are extracted properly even if the structure is padded. Okay, it's unaligned and not packed. It is getting padded and the right values are coming out. But the moment you come here and we are accessing this array with these values, we will see that it's not behaving the way it should. So array size is, let's see. So we'll see the array size. So array size is 12 instead of 9. So that has been padding. And then first element is AA. That is okay. Second element is DDCC and it should be BBCC, right? So we are seeing that there is a problem here. Though if we create a structure from this and then assign a pointer to that structure and then fill it up, then we'll not see this problem. So you see the difference here. Third element, fourth element, all of them will be pushed out by 1 byte. So to go around the problem, what we need to do is we need to, if we have a structure like this, if the structure is this way indeed, then we'll have to go around the problem by, we'll just add an attribute called packed here, and this will leave the structure as it is. So the compiler is not going to pad the structure at all. Okay, so this structure size is 9 bytes. So it will be more difficult. There will be more code to access the unaligned, non or unaligned word addresses here. But then we have instructed the compiler not to pad this. So at the cost of the code complexity, this structure is going to be anyway accessed as it is. Okay, so let's put the name there. So let's put the name of the define here. So not that, Control V. Okay, so see the beauty of define here. So we are just that is the Mac hash define. So we are just putting the structure name here, and it is propagating right across. Okay, so again, let us do the same exercise, but then the data widths are also the same, so we need not worry about that. Here we will have all of them as when we are extracting the data, so there's no harm in having them as UINT32T. When we are extracting from this structure, aligned structure, we only need to change the values here. I mean, if we had made it UINT32_T also, it wouldn't hurt. But nevertheless, let's put it for debug and see what's going on. So let's step through. Again, we are filling the structure with some values, the same structure with some values. And if you could see, it took a little longer to move from here to here, third element and fourth element, because I think because of the lack of alignment here, it will take a little long to fill the structure. Maybe, but I may be completely wrong here. So now we have filled the data here. So if you look at the structure space data, So space data has A, B, B, and so on. So all of these elements have gotten filled up. And then when we extract the values, first read, second read, third read, fourth read, we have APB. Fourth read is ABB. Okay. Now we have, let us see the structure, size of the structure now. Okay. So next line is the size of the structure. That is, so array size of structure. So if you see that, now the size of the structure has come to 9 bytes. Okay. So padding is not happening here. So we have given the attribute to be packed. So it is not padded. So when it's not padded, let us see what data is extracted. So let's see the first, second, we were facing an issue here, right? So first, second, third, and fourth, let's see what. So first is AA. Second is BBCC. Okay, so like we should get, previously we were getting CCDD, if you remember. Now we are getting BBCC because we have structure is packed now. Okay, so it is hitting the right places. Third, it is DDEEFF11. So it is ABBCC DDEEFF11. Okay, right? It's correct. And then the last one is 3322. 33 and 22. So you see this, when you declare it as packed, the structure is rightly accessed. Now the problem with packed, as I said, is when you instruct the compiler to not word align, then the processor has to work harder to extract the data. But then if you need to assign a structure that way, you have to do it. But try to keep it word aligned as much as possible. And if you see the registers that you have in Cortex M4, if you see the register banks, even without packed, all the registers are declared and they are all word aligned, and that's how probably the register bank is designed, so that the structures don't have to put a packed attribute like this. But nevertheless, this is a good thing to know, because this is something that many developers face problems with. Now, in the next video, let us quickly go through the header file. That is this header file. That's the STM32 memory map.h. So we'll have a look at the memory map, and this will more or less give us an idea of what is situated where and what are the different peripherals that we have for this particular processor. So this is for the STM32F11XE8. So different processors are going to have different header files. This is the only thing that we are going to use from CMSIS. Apart from this, we are not going to use anything.